Welcome back everyone, this is Advanced SQL. Hi there, long time no see. This is the next video in the Advanced SQL series. You see there is a new backdrop down there. This means an entire new chapter is starting, and what a chapter it will be. It will be chapter 6 on recursion. This will be the core of the lecture, the core of the course, and it will change everything. And well, what I mean by that, let's get into the meat. Okay, so it's chapter 6, recursion. We will add one construct to the SQL language that we've discussed so far, and that construct will change everything in a particular sense. SQL has already been a very expressive data-oriented language before we entered this particular chapter, right? But this is not but SQL has not been designed as a general purpose programming language, and that's actually for good intentions. You will never be able to write a SQL query that loops forever. You could easily do that in your favorite programming language, your general purpose programming language, but you would not be able to do that in SQL. Any SQL query will terminate regardless of the size and the contents, the schema, and the number of rows, the cardinality of the input tables. Okay, SQL can also be evaluated efficiently, right? With efficient evaluation, we refer to the space and time requirements that you will face when you evaluate your favorite SQL query over any input data. So let's see if we formulate a query over table T with C columns, okay, and R rows. So that would be C times R cells in table T. The worst thing that can happen to us that a SQL query over this particular table will take this space and time. This OR to the power of C space and time requirements, right? So the worst thing actually that we could do in this particular SQL query is to look at all the columns and form the Cartesian product of all the values in one particular column with all the values in all the other columns. So that would be the worst that we can do. So any value, any cell is combined with any other cell, that would lead to space requirements and time requirements that is in this class OR to the power of C, but that would still be a polynomial effort that we are investing here. Right, so if this is the limit of what space and time usage can be, then this means that there is some tasks that we simply cannot express using SQL, at least in the SQL dialect that we have discussed so far. So, for example, the computation of all the subsets of rows in a table T would, of course, yield a result that's exponential in size of the rows in T, of the cardinality of T, right? It would be 2 to the power of r rows that we would have to generate. That's just not possible with the SQL dialect that we have described so far. Okay, so and as I mentioned already, we will change all of this in the upcoming chapter, in the upcoming discussion. Right, so what we will take is really a giant step for SQL. We will add recursion to the SQL language. Okay, and this indeed changes everything. It's the addition of one more construct to SQL, but what we end up with is a different beast. So the expressiveness, for example, once we add this recursion, or as we will see, iteration construct to SQL, what we have in our hands is indeed a Turing-complete language, right? So Turing-complete means that there is no problem out there that the computer can express and actually compute the solution for us that we couldn't express in SQL. So the question of, hey, could I do that in SQL actually? Well, the answer to that particular question would now always be yes, once we add recursion to the SQL language. It SQL would be just like your general purpose programming language. It just can compute and express everything. Whether you want to do that, whether you want to map any problem out there to a particular SQL query that can compute the result for you, that of course is a different question, but it's that same question for any language out there. So there are some problems that you would better map to one particular language one than another language two. And of course, it's the same thing with SQL. SQL could do the job for you, but whether you would like to map everything to SQL, that's a different question. As we will explore in this chapter, there's a wide variety of problems that have very elegant, very compact, and very readable expressions in SQL, and we will study a number of them in this chapter. That's also the reason why this chapter is, I think, the most extensive chapter in the entire course. But be aware, this is not to say that anything now should be mapped to SQL. But lots of problems out there can and maybe should be mapped to SQL. All right. Regarding efficiency, well, this is probably the largest warning sign that you will see in the entire course, in the entire slide set. Well, we are no longer guaranteed that queries will terminate. I can promise that during this particular study of the material in this chapter, you will write queries that will just not terminate and run forever. It will just happen. It happens to me all the time. This prompts me to then have a closer look at the query, rewrite it, and then produce a terminating query. That, of course, is our ultimate goal, but it will just happen. There is no guarantee for termination anymore. And the evaluation with polynomial effort, well, of course, we cannot promise it anymore. If it's true that we can compute any problem, so for example, the subset generation problem, the subset of rows problem that we've mentioned on the previous slide, we can now do that. But of course, already the result will be exponential in size, and so will be the runtime. Okay, so all of this sounds like a pact with the devil in a sense, and maybe it is, but the payoff is magnificent. So what you get here is a really expressive data-oriented language that can compute anything for you. And I can only recommend that you take the time and study the stuff. It's really powerful. All right. And that's exactly what we would like to do here. So how does this new construct look like? It comes in the form of a common table expression. And we have seen that already. These CTEs, the common table expressions that were introduced by the keyword with, simply by with. We will now extend this to with recursive. All right. So with recursive is the indicator that the next block of queries is in fact a recursive query that can compute anything. All right. So the syntactic form of such a recursive query would then look like this. It would be just a common CTE query block introduced by with recursive in this particular case. All right. In this common table expression, we would of course define common tables, right? So this is one table, this is another table. We could define n such tables, and these would be the n queries that define the contents of these particular n tables. All right. The difference to the normal common table expression is in the recursive common table expressions, all these queries, this query, and this query, and also this query, the final query, the post-processing query, all of these queries may refer to any of these tables. All right. So we had the constraint that in a normal CTE, queries could only refer to tables that have been defined prior to this particular query. This is not the case with the recursive construct. Any query that we define here can refer to any of the tables TI that are being defined in this with recursive common table expression. All right. Of course, the post-processing, the final query here, can of course refer to all of these n tables T1 to Tn, but it has always been like this. Okay. The one particular interesting observation is that now any of these queries Qj may of course refer to itself. Qj may just refer to Tj itself. All right, so this is really a recursive reference, a self-reference of a query to the table that is currently computed by this query. Okay, so right. Mutual references are also okay. So if Q1 refers to Q2, then Q2 may refer to Q1. All of this is possible now with recursive common table expressions. If you are versatile in functional programming languages, there is a construct in FP language that's called letrec, or the recursive let construct. And well, the visibility and the scoping rules that we've just sketched here for this recursive common table expression are much like the letrec visibility and scoping rules that you will find in functional programming languages. Okay. All right. So this, of course, is the most intriguing part, that query Qj may refer to the result that it currently computes. Okay, and this, of course, this leads to this recursive behavior in queries. Let's have a closer look at this. Okay, so what would be the shape, what would be the syntactic shape of such a self-referential query? Right, so this would be one such recursive common table expression, and I have simplified it in the sense that only a single table, a single common table is defined here only. But this suffices to already express recursion. Okay, so of course this common table will have a schema with k columns, as you can see here. Nothing unusual so far. It will of course have a query body, a body of SQL construct that defines the contents of this particular table, right? Later on, I can then refer to this computed table T to do some post-processing and generate the final result. Nothing special so far. Okay. The inner body of this particular query has to take on a particular shape, a two-part shape. There's this first part, the base case query, Q0, and this recursive part, the Q loop or Q recurse, or the self-referential part of the query. Both parts are separated by this union or union all operator. One of both union or union all has to be used here. Okay, and we will later see that this using the separator union here really makes sense from viewpoint of the semantics of this construct. Okay, so it's a two-part query. The first part would be the base case query, which is evaluated exactly once. Okay, so Q0 will emit rows that, of course, have to adhere to this particular schema. And this Q0 query will be evaluated once. All of the rows that Q0 will be emitting are part of the result of the with recursive defined table T. All right. Then also the Q loop, the Q iterative, the Q recursive part of the query is being evaluated, since at this particular point we already have produced some rows using Q0, namely. This recursive part of the query may already refer to these rows. You see that I've indicated this here. This recursive part of the query may refer to the table T that we are currently defining itself. Okay, right. So Q recursive may refer to any table in the database, of course, but it may also refer to the contents of table T. What exactly it will find there, we will explain in a minute, but this is the recursive, the self-referential part here. And this recursive part of the query is evaluated iteratively or many times. So this part is evaluated once, the Q0 part. This part is evaluated many times. And all the rows that are being produced here, we will make this more concrete in a minute. All the rows that are being produced here are added to the overall result table T. Okay. At one point, we will stop this particular iteration, right? Then all the rows that have been accumulated in table T make up the result of the overall recursive common table expression, and they are passed on to this final query to do the final job here. Okay, so base case query evaluated once, recursive part query evaluated many times. The rows that are produced by both are thrown into one pot to make up the final result of the entire with recursive common table construct. So if we have a closer look at the semantics and abstract from the syntax here for a minute, then that would be one attempt to sketch the semantics of this construct. This looks intimidating, but I think it's not too bad if you read this stuff from right to left here. Okay, right. What the overall result of this table T of the entire common table expression will be is, of course, it will contain the rows produced by Q0, as I told you. The rows produced by Q0 make up the first contents of table T. Over this particular contents, we will evaluate the recursive query part the first time. Okay, so the result of Q0 is seen by the recursive query, and we will do our recursive evaluation for the first time. All right, so this will lead to a result. You find that result here again. And on this particular result, we will apply the recursive part of the query again. Okay, so now there's already two invocations of this recursive query part, right? We will continue to do that. Given this intermediate result here, all right, we will pass it on to another invocation of the recursive query to produce more intermediate results. All of these intermediate results, as you can see, are being collected using set union in this particular case. So when you look at the union below here, this is how we form the entire overall result. And as I told you, this is properly reflected by this union keyword that we use as a separator between the base case and the recursive part of the query. All right. We will continue to do that. We will continue to do and collect all these intermediate results until there is some halting criterion, some stopping criterion that we will explore in a second. Once we've reached that, then it's time to evaluate this final post-processing query queue. So I'm looking at this guy and at this guy. These are the same. I evaluate this post-processing query once, and it will of course see the entire collected result that we have accumulated so far. So this would be the semantics of this self-referential query. Okay. There's now the question of, well, when would you stop? What's the stopping criterion? When would you stop with these repeated evaluations of the recursive query? Here, the second part after the union. Okay, and the answer to this is in the operational semantics of this recursive common table construct. And I've tried to reproduce that for you here on the next slide. This would be a proper semantics of the self-referential query. We are talking about the union variant now, okay? I told you you could either use union or union all to separate the base case query and the self-referential recursive part of the query. Here we are talking about the union variant because the semantics of the union all variant are subtly but crucially different. Okay, so this is the first part of the semantics. It's the union variant, the set-based semantics variant first. Okay. So indeed, let's look at the semantics here and let's look at this divider because this divider tells us that this box gives you two equivalent versions of the semantics. You could either look at the left-hand side or at the right-hand side of this divider. You will find equivalent descriptions of the semantics. This would be more the iterative imperative state-based version of the semantics, you see that we are assigning values to variables here and then change them later. This would be the functional version of the same variant. So both programs compute the same thing. You can look at both variants and both will yield the same result. So look at the left hand or the right hand side of the divider, whatever you can read best or what suits you best. Okay, so let's look at the left hand side of the divider. Of course, the semantics of our recursive common CTE are based on, of course, the base case query and the recursive part of the query. These are the parameters of this little routine that explains the semantics of our query. Okay, so we will use a variable r here. Variable r here will collect the overall entire result. You can see that I'm returning r here as the final result of our function iterate. Indeed, r forms the final result. And as we've already discussed, the evaluation of Q0, the single evaluation of Q0, forms part of the result. And we can already see that here this assignment makes sense, I would say. Then there is a second variable t, which reflects the rows that have been added to the overall result during the last iteration. Okay, we will perform many iterations of the recursive query part. Well, in row T, you will find those rows that have been added during the last iteration. So when we enter this entire routine, there has been no iteration, but there has been a iteration of Q0. So we define the result of Q0 as the initial result of the first of the zeros, say, iteration of this entire query block. Okay, right. As long as this last result that we've computed is not empty, probably it will not be empty in the first iteration here because Q0 will probably not yield an empty result. If it does, then everything is done already. Then the entire CTE will return an empty result. Okay. If the last iteration did not yield an empty result, well, then it's time to invoke the recursive query once more. In this case, it's the first time, but in general, it will be the next iteration, the next invocation of our recursive query. As you can see, and this is super important, the iterative part of our query, the recursive part of our query, is invoked on the rows that we have found in the last iteration. Okay, so this is T here, not R. Okay. So the recursive part of the query is evaluated over the rows that we have produced in the last iteration. And as you can see, everything that we have produced before, everything that we have already collected in the result is being removed from T. We don't want to discover, we want to produce the same results all over again. Okay, so Q recursive can do its job. And the new rows, the newly discovered rows that we have not seen before, they make up the result of this current iteration. Okay, so this is super important. So only the new rows, only newly discovered rows that we have not seen before are actually admitted into T here. Okay, of course, these are valuable new insights, new results that we have collected, and they are, of course, added to R now. So we maintain our overall result and add the new rows T to R. This is indeed a disjoint union. Well, of course, it has to be, because anything that had an overlap with R has just been removed. Okay, so all the new stuff is being added to R, right? If we indeed have found some new stuff, if we have found new rows that we have not seen before, then it's time for a new iteration. And everything is performed again. At one point, we hopefully will find no new rows during the iteration. Okay, there will be no new rows discovered. At this particular point, it's time to end the entire process. This is the answer to our question, hey, when will the whole thing stop? Once we cannot find anything new, produce no new results, Then we are done with the iteration, and R is our overall final result. All right, so this set difference here really makes the difference, pun, okay, and it implements this semantics. Only the new rows found in the last iteration are being fed into the next iteration of our recursive query part. This is the semantics, right? And you find the same stuff over here. You would just invoke the recursive recurse function with an accumulated result of Q0 in the first invocation, and we would then maintain this this accumulated result on recursive calls here. And as you can see, indeed, we would remove everything that we have already found in the result from the evaluation of the recursive part of our query. Right. So this is the semantics. This is the semantics of our recursive query construct. Right. So I think let's call it the day for this particular video here. It had been long enough, almost 30 minutes already. This is the basics. This is the basics of recursive query relation in SQL. I don't think that we have to add much on top of that. Well, of course, we have to talk about the union all variant, which will look almost like this, which will be subtly different. But all of the rest of this chapter, all of the rest will be considered with cool use cases, cool consequences of the availability of with recursive common table expressions. All right. And I think it's, well, that's a construct that is not too complicated. All right, once you have wrap your head around that, but the payoff, as I told you on the previous slide, is magnificent. And I cannot wait to explore the consequences of the availability of recursion in SQL with you. I hope you stick around. I think it will be worth it. See you soon. Bye-bye.